In this lesson, we're going to look at a very interesting example that's often presented in the unit on universal gravitation for a number of reasons. It's a very good illustration of the inverse square law, as we're about to see, but it's just a neat problem to look at. Not very practical because we're talking about tunneling, as it says here, boring a hole through the center of the Earth, not even close to possible. The Earth gets very hot very quickly as you drill down into the Earth, so not practical. But the first thing we want to look at in our not practical but interesting theoretical problem to look at is, will the mass, if dropped into this hole that we dug through the center of the Earth, will it fall at all? And the answer is yes, because all of the conditions for Newton's law for universal gravitation are satisfied. We have an M1, the Earth, we have an M2, the mass we're dropping, and we have a center of mass to center of mass distance. So yes, it will fall into the hole. What we want to do first is calculate the gravitational force as a function of this little r as the object falls into the hole. Now, the first thing that we are going to see before we get involved in the mathematics of that is that, and please absolutely get this into your notes, that only the shaded M prime is going to contribute to the gravitational force. This region, which if you could kind of gray that in even darker a little bit and call that the shell, we're going to see that the shell does not contribute to the gravitational force, and we'll see why on our next page. And this is where this example is a very good illustration of the inverse square law and understanding the implications of having an inverse square law and a spherical geometry to deal with. So let's go to our next page of notes. All right, on this page, what we are looking at, to clarify, is if we put a mass M1 here at this point S, this start point or source point. So put an M1 here. What we want to do is look at calculating the force at this point as a function of r away from the point. And the first thing we are looking at is just having a unit mass m, a distance 1 meter away, and that unit mass m, one distance away, gives us what we're saying is a unit force here. Well, if I want the same unit force to be a radial distance, and my m, I'm making a point particle here. So if I want the same force on M1 at that position at a distance, a radial distance of 3m away, then hopefully you can see that that requires 9 mass pieces, all having a radial distance, and that's why it's now the surface on the surface of a sphere, because it's a radial distance away. They're all a radial distance away, so it's making a sphere surface. And that's what would be required to have the same force. Well, hopefully that makes mathematical and geometric sense to you, because if it does, then you absolutely understand how it is that same M1, in our case the mass of the object dropped into the hole, will not be affected by the shell. So the shell region, and what we're looking at here is, let's say we could hollow out the Earth. So we're just looking at a shell of the Earth. So the mass is just the shell, there's nothing inside. If I put you inside this hollowed out Earth, believe it or not, there would be 0 gravitational force on you. And it is because of the explanation up here that illustrated the inverse square law. So if you were, for example, a distance 1 meter from the top surface, that would correspond to a radial 1m. If it's a 4 meter diameter inner circle that we're looking at here, That means we have 3 meters on the other side, and you would indeed have the 9 m's here that would cancel out. And I showed it for this one orientation, but as we would go around, that orientation would hold. So we would just keep going around with an M and a 9M, another M and a 9M. So there would be no net force. And that is the most important thing. You will not have to go through an inverse square proof like we have here. But you do need to know there is no force inside a hollowed out shell. Okay. So the only thing that contributes to the gravitational force pulling this mass little m to the center is what I have designated as the m prime. So it starts out as the full mass of the Earth, but then gets smaller, as it's shown here, as the object falls in. And the trick to this problem is to recognize that you are going to use constant density. We are assuming the Earth is a perfect marble with uniform density throughout. So the total mass of the Earth divided by the total volume of the Earth, a sphere, 4/3 pi r cubed, is going to equal our m prime mass divided by its volume, 4/3 pi little r cubed, and voila, we get some very nice cancellation with our 4/3, our pi, and we get this expression. M prime is mass of the Earth divided by radius of the Earth cubed times r cubed. We are going to plug that in for this m prime here. And that's all we've done. We've plugged that in for the m prime. We have some more nice cancellation here. We get the r's on the bottom cancel out totally, leaving one r on the top. Notice everything else here is a constant. So we have force equals negative a constant times position, and we're going to see that that is indeed our simple harmonic motion condition. But as we would start at the Earth and fall radially inward, we would get a linear decrease. As if we started at the center of the Earth and worked our way out, we would get a linear increase up to a maximum force, G capital M, little m divided by r squared. And then, of course, as we leave the surface of the Earth, it drops off as 1 on r squared. So this is our force due to gravity. As we go from the center of the Earth radially out, or from the center of the Earth radially in and outward from the Earth. The other very interesting point here that is always part of this question is that since we have a force of the form F equals minus kx, we would indeed get simple harmonic motion, would be the result of the overall motion of this particle. In other words, we would drop it into our hole. It would accelerate, have its maximum speed at the center, decelerate, come to a stop at this end, and it would just oscillate back and forth, theoretically. So really interesting problem. Again, please always know, even without the derivation, that if you do have a hollowed out shell of a mass in the shape of a sphere, you get F equals 0 inside the shell. Other than that, please make sure you make your annotations as usual, and we will move on.